Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to go ahead and continue our conversation on acid and base reactions by looking at percent ionization. So until now, when we've been looking at acid-base reactions, we've been focusing just on the amount of hydronium being produced. So how many protons have we produced? However, it turns out plenty of reactions don't care about protons. It turns out that a lot of our conjugate bases can be quite valuable chemicals in their own right. They can react and make solids with make ionic compounds. They can actually even just play an important role in biology, like phosphates. So if I'm going to go ahead and determine the amount of conjugate base produced, we need to go ahead and figure out this ratio of how much of the base fell apart versus how much acid I generated. This can be done by looking at a parameter called degree of ionization, which we're going to represent as an alpha. So this is literally just going to be how much conjugate base I produced versus how much acid I introduced. So again, one of the big things to note is this is going to be the initial concentration of the acid versus an equilibrium amount of conjugate base. So these can actually be under different conditions and give you some very fun results. However, it's also important noting that if we assume that the amount of hydronium present is fairly low, the amount of the equilibrium concentration and the hydronium concentration should be equal. And so this actually has its own power because it means that if you go ahead and add a certain amount of acid, it could be possible to determine the equilibrium concentration of the conjugate base, and thus this degree of ionization, simply by measuring the pH. However, much more commonly, we have to go ahead and figure out this parameter just by knowing the acidity of our solution, so it's pKa, and the initial amount of acid added. So in order to do this, we're going to need to go back to our ice table for a weak acid. So let's go ahead and do a common species, formic acid. So formic acid is fairly straightforward. It's a nice, simple oxyacid. It's quite potent with a pKa just under 4, so about 3.75. And it's also it also gets its name from ants, which in Latin are formates, because formic acid is the key component of many ant venoms. It's what gives them that sting if they end up biting you. So if we have formic acid, it will decompose to make formate and release protons. So let's go ahead and try and figure out exactly how much formate will end up getting produced. So we'll go ahead and start with our ice table. Again, ignoring water because it won't show up in the equilibrium constant. We have initial concentration of 1 molar formic acid and 0 of everybody else. We're consuming formic acid and producing formate and water, or protons. So then we have a nice simple equilibrium. However, let's go ahead and make the math a little easier by assuming that X is going to be fairly small. In other words, that we're not going to be consuming that much of our formic acid. This makes it a little easier to determine both the concentration of our formate and our protons, as it will simply be, as the X for this one can simply be given as the square root of the equilibrium constant times the initial concentration. So when we do the math, it turns out that this is about 0.013 molar. So it turns out we've got a bit of composition. So if you want to get a more accurate number, feel free to run through the quadratic equation and see how much it deviates under these circumstances. However, for sake of time, we'll go ahead and use this as the concentration of formate. And we're going to go ahead and divide it by, here's the key bit, the initial amount of formic acid, which in this case is just going to be 1 molar. So when we do this, it turns out that our percent ionization is going, our degree of dissociation is going to be 0.013, and our percent ionization will just be that number times 100. So it's about a 1% decomposition. So I've got about 1% of my formic acid decomposes or breaks apart to make formate, and 99% of it stays intact. This is going to be true for most weak acids. Most of it's going to stay intact. A small portion will break apart. However, one of the interesting things when looking at percent ionization is it actually becomes dependent upon the initial amount of acid added. So let's go ahead and try and determine this percent ionization for 0.1 molar formic acid. So most of the math is going to be the same. Only big trick here is now my initial concentration is going to be 0.1 molar, and my equilibrium will be 0.1 molar minus X. And because we're still going for speed here, let's go ahead and assume that most of the formic acid stays intact. And so then if we're solving for X is going to be about 0.041 or 0.041, which again is about as much as we had previously. The pH is just going to be a little bit weaker. However, it turns out when I'm looking at the degree of dissociation, now it's 0.04. So we haven't released quite as many protons, but we had to break up more of our acid to do it. Because now when we go ahead and turn this into a percent ionization, we went from a 1% ionization for 1 molar to a 4% ionization for a 0.1 molar formic acid solution. Now, this is kind of interesting, but it makes a certain amount of sense. Because as I add less and less of my formic acid, it turns out that a larger portion of it has to break apart even to maintain similar acidities. Because in this case, our solution won't even be as acidic as it was before, but it's still in the same ballpark. And that's one of these important features. As I add less and less acid, my percent ionization will go up and up. And you kind of can see this in a graphical form. So let's go ahead and say that I've got a fairly strong acid. Now, if I have a fairly strong acid, say a Ka of 10 to the 1, so this would be straight acidic, or even a Ka of 1, which is our very definition of anything greater than this is a strong acid. They completely disassociate pretty much until you start hitting 0.1 molar, at which point that pH starts getting pretty close to the pKa, and less of the acid is going to need to break up to get us in that right ballpark of the pH. Now, the same feature happens with almost every acid, where they'll tend to break apart. And then as you start getting in shouting distance of that pKa, less and less of it will break apart. So it's less pronounced for these strong acids, which generally will ionize more or less to completion. However, if you end up with a fairly weak acid, a Ka of 10 to the negative 7th, well, I'm sorry, but you're almost never going to be able to make use of dropping the X. We're always going to have to do the quadratic equation because the degree of ionization almost never ends up exceeding 50%. Most of the acid will actually stay intact, and only a small portion of it will break apart. So this is something to keep in mind with when we can make our approximation. Large Ks, system almost always breaks apart. Smaller equilibrium constants, very little of the acid breaks apart because it's frankly not that acidic. And we'll be talking about this a lot through the remainder of this chapter and going into the next. However, so far we've mostly been looking at how much of an acid breaks apart. Next time, we're going to go ahead and take another look and figure out how we can find the pH of a base. Until then, take care.